In this week, we will first focus on the dummy variables. That is, the variables can either take the value of 0 or 1. First, let's check the situation that the independent variable x in the simple linear regression model is binary. In econometrics, binary variables are also commonly called dummy variables. Recall that the simple regression model says that the two variables x and y follows this relationship. The population regression function is that the expectation of y conditional on x is equal to beta 0 plus beta 1 times the independent variable x. Notice that we can take the expectation because of the random sampling assumption. So the expectation is taking on the random sample x and y. Beta 0 and beta 1 in the population regression function are fixed parameters. Once we collected a sample xi, yi with n observations, we can run the OLS regression to estimate the coefficient beta 0 hat and beta 1 hat. The sample regression function says that the fitted value for the observation y hat is equal to the beta 0 hat plus beta 1 hat times the x. Remember how we obtained the best beta 0 hat and beta 1 hat. We minimize the distance between the fitted value yi hat and the observation yi, and the distance is measured by the sum of squared residuals. Notice the difference between population regression function and the sample regression function. The population regression function describes the true relationship between x and y, which we do not know. The sample regression function is the relationship we get from the data at hand. Ideally, we want the sample regression function as close as to the true population regression function. That is, beta 0 hat is a good approximation for beta 0, beta 1 hat is for beta 1, and similarly the fitted value should be very close to the expectation of y conditional on the x. So what will change for the population regression function and the sample regression function if now the independent variable x is binary? For the population regression function, if we know the independent variable takes the value of 1, then the conditional expectation of yi is the average of yi in population with x equal to 1. Similarly, the conditional expectation of yi given the dummy variable x equal to 0 is the average of yi in the population with x equal to 0. Notice that these two conditional expectations are all about random sampling. If we further plug the population model for yi into these two conditional expectations, we can simplify them. The conditional expectation of the outcome variable y given x equal to 1 is beta 0 plus beta 1, and the conditional expectation of the outcome y given x equal to 0 is simply beta 0. So the beta 1 is the difference between these two conditional expectations. If we know all the observations in the population, beta 0 is the average for y for the group that x equal to 0, and for the group that x equal to 1, the average for y in the population is beta 0 plus beta 1. We also call that the beta 1 is the population treatment effect. It captures the outcome difference for those who taken the treatment, which corresponding to x equal to 1, and for those who do not take the treatment. But the interpretation for beta 0 and beta 1 are all about the population. We cannot observe all observations in the population. We often get a sample xi and yi and estimate these two parameters. We often obtain an estimate for these two parameters given a sample xi and yi. We can similarly apply the OLS method to obtain the estimator. If we simplify the beta 0 hat and beta 1 hat from OLS for binary x, we will see that the beta 1 hat is called the sample treatment effect. It's the difference of the outcome variable y between these two groups, one corresponding to the treatment group and the other one is the control group. And the beta 0 hat is the average of the outcome y for the control group. Also notice that these two equations only hold for the simple linear regression model. If we have additional independent variables besides the binary x, we cannot estimate beta 0 hat and beta 1 hat based on the sample average for different groups. Consider the following multiple linear regression model for which the independent variable include education, which is a continuous variable, and the gender, which is a binary variable. If we let the binary variable x takes the value 1 for female and takes the value 0 for the male, then the parameter delta 0 measures the difference in hourly wage for women and men given the same level of education and the same error term u. Under the assumption of zero conditional mean, that the error terms is not correlated with any of the independent variables, then similarly, the parameter delta 0 equals to the difference between two conditional expectations for wage. One is for the female group and the other one is for the male group, and they have the same level of education. That means, given that females and males have the same level of education, delta 0 is the expected wage difference between female and male. Notice that the parameter delta 0 is also from the population. If we plot the population regression functions, we can see that the parameter delta 0 measures an intercept shift between male and female wages. The slope for education is beta 1 for both male and female. Therefore, these two lines are parallel to each other. If delta 0 is negative, we will see that for each level of education, males earn more than the female, and this wage gap is fixed to be delta 0. Males here are chosen to be the benchmark group or base group. That is, males are the group against which the comparison will be made. We could also estimate the following model for the wage. Now the binary variable is the male. For the x equal to 0, it corresponds to the female group, and if x equal to 1, it's the male group. In this case, female is the base group, and the male is the treatment group. These two regression models are equivalent. Alpha 0 is the intercept for the base group, which now is the female group, and alpha 0 plus gamma 0 is the intercept for the treatment group, which corresponding to the intercept beta 0 in the previous model. If we use a dummy variable to indicate a policy intervention, The base group is often the one that is not influenced by the policy and is often coded as 0, and the treatment group is coded as 1, indicating that the group will be influenced by the policy. Another question is, can we estimate the econometric model that include both the male and female dummies? That is, wage is regressed on male, female, and education. Using two dummy variables would introduce the perfect collinearity because the value for the male dummy plus the value for the female dummy always equal to 1. That means the male is a perfect linear function for the female or the otherwise. Let's check the gender wage gap with some data. How can we test there is discrimination for females' wage? We use the dataset wage 1 and run the regression of wage on explanatory variables, include a dummy variable for female, education level, experience, and tenure. It includes 252 females, which takes 48% of the whole observation. Here is the regression results for the multiple linear regression model. We are particularly interested in the coefficient for the dummy variable female. This coefficient measures the hourly wage gap between a male and a female who have the same levels of education, experience, and tenure. According to the estimation, if we take a female and a male with the same level of education, experience, and tenure, the female earns on average $1.81 less per hour than the man. Recall that these are the wages for 1976. Since we have already controlled for other factors like education, experience, and tenure, this 1.81 wage difference is purely due to gender or factors associated with gender that we have not controlled for in the regression. It's not because of other variables we've already included in the regression. What if we do not include other explanatory variables and only regress hourly wage on the female dummy? Is the wage difference smaller or larger? Here is the results for the simple linear regression model of wage on the gender. The intercept coefficient is the average wage for men in the sample. So men on average earn $7.1 per hour. The coefficient on the female dummy is the difference in the average wage between women and men. Therefore, the average wage for women in the sample is 7.1 minus 2.51 equal to 4.6. Therefore, the hourly wage for women is $4.6 per hour. The t-value for the coefficient beta 1 hat is quite large, so the wage difference is statistically significant. Of course, the $2.51 wage difference is also economically large. Compared to the previous regression model, now the estimated wage difference between male and female is larger because this simple linear regression model does not control for the differences in education, experience, and tenure. And all these factors are quite low on average for female than for male in this sample. So we have larger wage gap because all other factors also contribute to the wage difference. When the dependent variable is in log terms, we have the percentage interpretation. Here for the same regression model, now the dependent variable is the log wage. The coefficient for the female dummy is minus 0.3, It means that the females earn about 30% less than the males for the same level of education, experience, and tenure. Dummy variables are also helpful in the case of ordinal data. Suppose we would like to estimate the effect of the city credit ratings on the municipal bond interest rate. There are several financial companies, such as Moody's Investors Service or the Standard & Poor's, rate the quality of debt for local governments, where the ratings depend on the things like the probability of default. For simplicity, suppose that the rankings range from 0 to 4. The 0 means the city has the worst credit rating, and the 4 being the best. This is an example of an ordinal variable, so we do not care like specific what this 1 rating or 2 rating means. We only care like 1 rating is worse than the 2 ratings, and the 4 rating is better than the 3 ratings. The question is, how do we incorporate the variable like the credit rating into a model to explain the municipal bond interest rate? One possibility is to just directly include the variable credit rating as a continuous variable. We have this regression model. It's the standard one as the multiple linear regression model. How do we interpret beta 1? The beta 1 is the change in the dependent variable MBR when the credit rating CR increases by 1 unit, holding all other factors fixed. But it's not clear what a 1 unit increase in CR means, as it is an ordinal variable. Is the increase from a 3 rating to a 4 rating the same as the increase from 0 rating to 1 rating? If it is unlikely that the credit rating has the constant effect on the bond interest rate, then this model that by treating the credit rating, which is an ordinal variable, as a continuous variable may be invalid. To deal with this changing marginal effect for different ordinals, a better approach is to generate dummy variables for each value of the credit rating. For instance, since there are 5 ratings from 0 to 4, we can generate 4 dummy variables. Let the dummy variable CR1 equal to 1 if the credit rating is 1, and otherwise it's equal to 0. Similarly, if the credit rating is 2, then let another variable CR2 equal to 1, and for all other ratings that is not equal to 2, then the CR2 equal to 0, etc. Then for the regression model, instead of having a single credit rating variable, which is a continuous variable, now we have 4 binary variables, CR1, CR2, CR3, and CR4. The base group now is the cities with credit rating of 0. If a city has a credit rating of 1, then the CR1 will equal to 1, and all other dummy variables will equal to 0. The parameter delta 1 is the difference in the bond interest rate between a city with credit rating of 1 and a city with credit rating of 0 when holding all other factors fixed. Similarly, the parameter delta 2 measures the difference in the bond interest rate between a city with credit rating 2 and the control group of cities with credit rating of 0. The parameter delta 1 do not necessarily equal to delta 2. If they are indeed different, it means the marginal effect of the credit rating on the bond interest rate will be different for different ratings. This approach to generate dummies for different values of the ordinal variable can be quite useful. For instance, here is a regression for the salaries for law school students and the ranks of the law school, controlling the Laset, GPA, the library volume, and the cost of the law school fixed. If we treat the rank as a continuous variable, the estimated coefficient here says that for every 1 unit increase in the ranks for the law school, the estimated salary will decrease by around 0.3%. But if you use this econometric model, you implicitly assume that this marginal effect for the rank over the salary will be the constant for different ranks of the schools. Another way is that we can create dummies for different groups of the ranks. Here we create 4 dummies to represent the rank for the law school. The control group is for the law schools who has the rank higher than the 60. If the rank for a law school is in the top 10, then the dummy variable top 10 will be equal to 1, otherwise it will be equal to 0. Similarly, the variable R11 to 25 equals to 1 if the ranks of the law school is between 11 to 25. So here is the regression results. We can check the coefficients for the different rank dummies. We see immediately that all of the dummy variables defining the different ranks are very statistically significant. Moreover, the partial return for the ranks over the salary are quite different for law schools belonging different rank groups. Based on the estimation results, we can answer questions like whether the top 10 law school will generate the highest marginal return for the salary compared to the other law schools, or we can also test the null-hypothesis that all other variables except for the law school ranks are jointly insignificant. I will leave this as exercises. You can try to do the hypothesis test and answer these questions with the linear hypothesis function in R.